Okay, good afternoon to all of you again. So, let us revise first what we have discussed so far in the compactness, and then I will move to the new results. So, compactness we have defined for any topological space X that says that if I am given a collection of open sets which cover the given topological space X and that cover maybe finite or infinite collection of open sets, then I can always find a subfamily of UI which covers the space X. The original family UI may contain infinitely many sets, but if X is compact, then we can always find a finite family from a given infinite family so that we can cover the space X. So that is basically the compactness. So it says that every open cover has a finite subcover, and we have seen some examples over the real line. So R is not compact space with respect to the usual topology because this open cover does not contain finite subcover. And next we discuss this particular set which has a limit point that if I have a set 0, 1, 1 by 2, 1 by 3, so on, which is a subset of R, then as a subset of R, it has a subspace topology coming from the standard topology on R. And with respect to the standard topology, whether X is compact or not. So that is the question. So let us, in fact, we proved that this is actually a compact space with respect to the subspace topology coming from R. So these two examples we studied, and then we studied subspace. What is meaning of cover of a subspace? The cover of a subspace is that instead of equality, we have a subset relation here. Y is a subset of union A alpha, and in this case, we have seen that if the star property is satisfied, then Y is a compact subspace of topological space X. Then we have seen some of the important results which I will use in today's lecture. So one result is that every closed subset of a compact topological space is always compact. So if you know some topological space X is compact, and if we have a Y which is a subset of closed subset of X, then Y is also compact. So this is regarding the subspace when it becomes compact. And on the other hand, we have a result which says that when subspace becomes closed. So if I take a compact subset of a Hausdorff topological space, then it is always closed set, right? So this way it is closed with respect to the subspace topology, and we have seen all these results which are very important, particularly the results that compactness is a topological property. That means image of compact space under a continuous function is always compact. And in the previous in the previous lecture, we discussed one example that if X is a non-empty set on which we have a cofinite topology, then it is always compact space. So we discussed two cases, one in which one case it is finite set and other case it is infinite set. So whenever we have finite set, then whatever topology we consider, it is always compact. And last result which we discussed in last lecture was tube lemma. So that we'll start today lecture with as an application of this lemma. So consider the product space X cross Y. So X and Y are topological space, and using that we can define product topology on X cross Y using topology on X and topology on Y. And with respect to the product topology, if I choose a point P in X in the first space X, P belongs to X, and assume that Y is a compact space. So if W is a subset of X cross Y, which is open and it contains this particular set singleton P cross Y inside that open set W, then we can find open set U of X. So P is element of X. So I will get an open set U of X, so that U cross Y is a subset of W. Alright, so whatever W open set is given which contains singleton P cross Y, I will get open set U of X such that U cross Y is a subset of W. So this is tube lemma. Using that we will show that the product space is compact whenever X and Y is compact space. So the statement of the theorem is that let X and Y be topological spaces. So they have a topology, and with respect to that topology, they are compact also. Then if X and Y are compact, then X cross Y is also compact. So X cross Y is compact with respect to the product topology. So in proof, we want to show that X cross Y is compact, and by definition, whatever space is compact, if we have an open cover, it contains a finite subcover. So that we need to prove. So let us start with the open cover of X cross Y, and then we'll find a subcover of that. So that will prove that X cross Y is compact. So let a family C, which is collection W alpha. So this family is a open cover of X cross Y. So what does this mean? This means that X cross Y we can write as union alpha W alpha, right? That is meaning of this. So now we want to apply the lemma, and in the lemma we have considered a particular set singleton P cross Y. So let us start with that. So let any point P in X. Then we have studied in one of the lecture that if I take the set P cross Y, then P cross Y is homeomorphic to Y. So P cross Y is so Y, if Y is for example in XY plane, if we take, then Y is Y axis. So singleton P cross Y is basically X equal to P line. So X equal to P line is always homeomorphic to the Y axis. So that is exactly meaning of this, but in the general setup of topology. So whatever topological space Y we take, singleton P cross Y is homeomorphic to Y, and what we know about Y is in the hypothesis it is given that Y is compact. So since Y is compact and compactness is preserved under continuous functions, so in particular it is preserved under homeomorphism. So we get that since Y is homomorphic to P cross Y is also homeomorphic, is also compact. So P cross Y is a compact space, and what is the relation between X cross Y and P cross Y is that singleton P cross Y is a subset of X cross Y, and for X cross Y we have open cover, so that will also cover P cross Y. So now singleton P cross Y is we know that it is a subset of X cross Y, and X cross Y is union of W alpha. So what we get is therefore W alpha is a cover of this subspace P cross Y, and P cross Y is compact. So actually it is an open cover. So I think I mentioned it is an open cover here. So it is an open cover. But now it is open cover of P cross Y, and P cross Y is compact. So now we have open cover of P cross Y, which is a compact, so it will contain a finite subcover. So therefore singleton P cross Y is subset of union of, so finite family. So let us call it W alpha k running from 1 to n. So where, so this finite family I will denote I will denote by Fp. So where Fp defined to be W alpha 1, W alpha 2, W alpha n be a finite open subcover of C. So C is the family W alpha. This is a finite okay, so finite subcover of P cross Y. So it is subfamily of C, but it is a finite open subcover of P cross Y. And so every point P we get this family Fp. Whatever point P I select in capital X, I will get this particular family W alpha 1, W alpha 2, W alpha n based on that particular point P. So therefore I am denoting it by Fp, because this finite family depends on uh, whatever P we are choosing, right? So now what we will do is we will consider a particular open set which is union of these W alphas. So let n be the set which is union of k1 to n W alpha k right? So what are these W alpha K? They are elements of FP, right? So since each W alpha is open, so therefore N is open set, right? So N is open set, and uh, what we know about N is union of W alpha, which actually covers singleton P cross Y, right? So this family covers P cross Y is a subset of N. So now we are in the situation of the tube lemma. So let us go to the statement of tube lemma, which says that if I have an open set W, which is a subset of X cross Y, right? So let us denote it by W itself instead of N. Let us denote it by W because it is union of W alpha. So whatever open set we are given which contains P cross Y, I can always find open set U such that U cross Y is a subset of W, right? So U cross Y is a subset of W. I can always find such a set U. So by by tube lemma, which we proved in the last lecture, we get there exists an open set, say UP of X such that UP cross Y is a subset of W. So in the tube lemma we are getting set U, but I'm denoting here the set by UP because it actually depends on the point P which we are choosing, right? So therefore for every point P we are getting an open set that we are denoting by UP. And once we get this set UP, what we know is that UP cross Y is a subset of W, and W is this family, right? And UP cross Y is a subset of W, which is union of W alpha K. This union of W alpha K is actually the cover of UP cross Y, right? So let us write down that. So therefore, union W alpha K covers UP cross Y. So therefore, basically FP is the family FP covers. FP is a finite subcover of UP cross Y, and this is true for all P belongs to X, right? Because we started with the point P belongs to X, right? So whatever we have discussed, that depends on which point P we are choosing. So for every point P, there exists a family FP, which is collection of finite sets from the family C, and this family is a finite cover of UP cross Y. And so every P we are getting UP, which is open set in X. So therefore, singleton P is a subset of UP for all P belongs to X, and this will give us that X I can write as a union of UP for each P belongs to X. So basically I got a open cover of UP is open in X, right? So that we already know, we have written somewhere that UP is open subset of X. So that is coming from the tube lemma. It is open set. So now we have open cover of X. We used earlier that Y is compact, but now we will use that X is compact. That is given in the hypothesis. So now since X is compact, the open cover UP of X has a finite subcover. So it covers a finite subcover. So that is we can actually write X as a finite union of the elements. So we can write it as union of finitely many UPs. So let me call it P1, P2, Pm, right? So this is a set which is a finite cover of X, finite subcover of X. And so this we are getting from the compactness of X, and then finally we will get what is X cross Y, because we are interested in finding the finite subcover of X cross Y. So X cross Y is basically union of UPL, that is equal to X cross Y. And then once again we can write this as that is equal to the union of L running from 1 to M UPL cross Y, right? So these two sets are same. So once we get this, then what we know is that all such sets UPL cross Y has a finite cover FP. So we have written here that FP is a finite subcover of UP cross Y, right? And once we have a finite subcover of each UP cross Y, so each UPL cross Y has a finite subcover FPL, right? For all L is equal to 1, 2, up to M. So in FP1 there are finitely many sets. In FP2 there are finitely many sets. In FPL there are finitely many sets. So when I take the union of all such sets, then what I will get is X cross Y is union L running from 1 to N UPL cross Y, that we already noted. And now each UPL cross Y has a cover FPL. So that means We can write this as the union of so what are the elements of Fp? We denote it by W alphas, right? So W belongs to FPL. Let us write by W belongs to FPL, W alpha L, union of W alpha L. So each FPL contains finitely many elements. So this is union of finitely many elements. And then again we are taking union from L is equal to 1 to M. So basically, so this is subset actually, right? Because UPL cross Y is subset of union of W alphas. So therefore, X cross Y has a finite subcover which contains elements of FPL for L is equal to 1 to up to M. So each of these set FPL has finitely many elements, and then we are taking union of finitely elements. So that is again a finitely many elements. So that provides us a finite subcover of X cross Y. So therefore X cross Y is compact. So so essentially product topology we did not use in this theorem, but surely we use in the tube lemma, right? So there we use uh, that the topology on X cross Y is product topology. So we get that open set U with the said property, and that is essential here. So what we proved is that whenever we have two topological spaces X and Y, then their cross product is always is a is a compact space if X and Y are compact, and it is compact with respect to the product topology. So in particular, if X and Y are the same topological space, then this theorem will give a corollary that X cross X is compact with respect to the product topology. And we can using mathematical induction we can prove X cross X n times, that is Xn is compact with respect to the product topology. So that means whenever X is compact, X cross X n times, that is a also compact space. So let us write down the corollary. So if X is compact topological space, then X cross X n times is also compact. So what do you mean by x n times as product topology? So product topology we have discussed, which is a basis that u cross v is open when u is open in x, v is open in y. So now here I have the cross the product Cartesian product n times, right? So that means I have the set u1 cross u2 cross so on n times. So this set will be the base in the basis of in the product topology, where each ui is open in X for every I is equal to 1 to up to n. So when we take n equal to 2, that is exactly the product topology on x cross y. But the same idea you can use n times, so we will get the product topology on xn. Or in general, we can define product topology on x1 cross x2 cross xn, where x1, x2, xn are topological spaces. So now we want to discuss continuity of the inverse function. So sometimes it is it is also known as inverse mapping theorem or automatic continuity. Of F inverse. So the statement is that let the the statement is that let f is a function from x to y be a bijective continuous function, and if x is compact, that means domain is compact and the codomain y is Hausdorff space. So x and y are topological spaces where x is compact and y is Hausdorff, then f is a homeomorphism. So what is given is that f is bijective function, it is continuous, but what we want to prove is that f inverse is continuous, because f is homomorphism if f is bijective continuous plus its inverse is also continuous, right? So that only thing to prove here is that f inverse is continuous, and we know some criteria to prove the function is continuous. So we can prove the function is continuous if its inverse image of open set is open or inverse image of closed set is closed, right? So that we have already discussed. So what we want to prove is that the claim is that f inverse is continuous, and to prove f inverse is continuous, we show that inverse image of f inverse of a closed set. So f inverse is basically the function f. So this is closed in the codomain whenever is open set in X, right? So because here we are not checking the function f is continuous, we are checking the function f inverse is continuous.
A is
So,
closed also.
right, you are right. So that is a closed set. Okay, thanks. So, so as you have mentioned that whenever we take A is a closed subset in X, we have to show the inverse image of that set is closed in Y under the F inverse function. So since we know that F inverse is F, so therefore we need to show that F inverse A is closed in Y when A is closed in X, right? So this is what we are looking. Sorry. So again, here it is f of a because f inverse is f. So this is what we are looking. We want to prove, and now we will use the theorems, several results which we proved uh, regarding the compactness, that closed subset of compact space is compact and compact subset of Hausdorff space is closed. All these things we will use here. So let us start with let AB. So this thing we need to show. So let us start with AB, and AB a closed subset of X, and what we know about X is that X is a compact space that is given in the hypothesis. So X is a compact topological space. So therefore we get we know that from a result that from result which we proved, we get that closed subset of compact space is always compact. So that means A is a compact subspace of X, right? So now A is compact. So and F is continuous. So what can we say about F of A? F of A is also compact using because compactness is the topological property. So since F is continuous and A is compact, from a known result, so this result we proved that F of A is closed. Sorry, F of A is compact and so F of A is compact subspace of the codomain. And what we know about Y is a Hausdorff space. So now F of A is a compact subspace of the Hausdorff space Y. So now we have a result that every compact subspace of a Hausdorff space is always closed. Right. So using another known result, we get Y is closed. Sorry, f of A is closed in Y. Right. So that is what we wanted to prove. We started with a closed set A of X, and we wanted to prove that f of A is closed in Y. Right. So this will prove that f inverse is continuous, and since f inverse is continuous and f is bijective and f is continuous, that is given in the hypothesis. So therefore f is a homomorphism. So this result is very important result in topology because it is related to the inverse function. So if we want to prove that some function is a continuous function, the inverse of some function is continuous, then it is only need to check that the domain is the domain is compact and the codomain is Hausdorff. If we can verify this thing, then all such functions which are bijective and continuous from a compact space to Hausdorff space will automatically, the inverse will automatically will be continuous function. So this is one of the important result of topological spaces.